Think back to when we were talking about friction and pushing boxes across garage floors. When we push those heavy boxes across the floor, it's a lot of effort, right? As the box becomes more active, so to speak, and its motion goes from nothing to something, our body gets tired from exerting this force on the box and pushing it across the floor. What is this currency of sorts that seems to be transferring from us to the box? As we push the box and we get tired, the box increases in its motion. Seems like we are losing something and the box is gaining something. In everyday speak, we might say pushing the box is a lot of work. Well, as it turns out, this word work is used in physics as well to describe what's happening, but it has a very precise definition in physics. So work, in physics, is a force applied through a distance. So work is capital W, and it's a force times a distance. And I'm going to write S, and S is typically used for displacement. So that would be like delta x here, as I've drawn here, like x2 minus x1. So it's a force times a distance. So specifically, it's the force applied in the direction of motion only that counts towards the work. So here I have the box is going to be moving from x1 to x2. So this would be like in the x direction. And the force is also parallel to that motion. So the force, every bit of this force is in the direction of motion. And so this would truly be just F times delta x, right? The displacement. But what if instead we had a force that was a little bit off from exactly in line with it, right? So what if we had our force instead, what if we were kind of pushing down on the box? So we're leaning over and we're pushing down on the box like this. Well, it's only the component of the force that's in the x direction that counts. So, right, we can figure out our components just as always, and we only care about this component. So that one there. So this would be at some angle, right? And so this would be F cosine phi in this example. So then in that case, a more precise definition of work, taking this into account that it's only the component of the force that's in the direction of the motion, we could write F S cosine phi, phi being the angle between F and S, right? So S is just the displacement, the direction of displacement, and F is the direction, the force. So this would be the angle between them. And we know from a few lectures ago that another way to write that more compactly would be the scalar product of F and S. So both of these are vectors, and this is not simple multiplication, this is the scalar product, or in other words, the dot product. And the product of or the result of a dot product is a scalar. So work is a scalar. There is an amount of work, not a direction of work. So work can be positive, negative, or 0. There's different scenarios here that describe how that can be. Okay. So if work, I'll straighten this out for you. If we have the force that has a component that is in the direction of displacement, then the work, if the net force rather, here there's only one force for each of these cases, but really we're going to talk about the net force. So if the net force has a component that is in the direction of displacement, then work is positive. If the net force has a component opposite to the direction of displacement, then work is negative. So how could that be, right? If you're pushing something this way, how could it be going that way? Well, it was already pushed this way, right? It already had some motion in some direction towards the right, and now you're pushing on it or pulling on it to slow it down. So you'd be doing negative work technically. This is kind of where the colloquial definition differs from the physics definition, because it's still a lot of work to pull something to a stop, but this would be negative work in physics. And then to do zero work, you just have no component in the direction of motion. So if you're pulling directly up on something, but it's traveling to the right. So this would be kind of like a normal force. If it was sitting on a surface, and there's gravitational force, and this would be like a normal force, and it's traveling this way, well, the normal force and the gravitational force are doing zero work, although they do exist. All right. So like I said, we're really talking about the net force here. And so if you have more than one force involved, then you just find, like we've done in the past, the net force vector. And then you multiply by the displacement. Or you find the net force vector, and then you multiply the component of that in the direction of motion by the displacement. So let's do a quick example just to show this. So let's see. So this is pretty much identical to things we've done in the past. We're just adding this extra thing where if we have a force being applied through a distance, then you just multiply by the distance. You multiply the component of the force that's in line with that distance traveled by the distance, and then you get the work done. And this is going to help us solve more complicated problems, so it's not just for nothing. So we have a tractor here. There's an image that goes along with it if you want to get a nice visual of what's going on. A farmer hitches their tractor to a sled loaded with firewood and pulls it a distance of 20 meters along level ground. The total weight of sled and load is 14,700 newtons. The tractor exerts a constant 5,000 newton force at an angle of 36.9 above the horizontal. Blah, blah, blah. Okay, so we've done problems like this before. First thing to do is identify what we're trying to solve for. In the end, it says find the work done by the forces. So we're trying to find the work, which makes sense since that's the topic today. The next step would be to draw a simpler diagram, and I probably would for this one. So it gives us all the stuff to do with this. The tractor doesn't really matter. So let's draw the load as that. And then we have a pull that's happening at some angle here, right? Angle phi. So there's some force like that. I'll just do that. And then it's on the ground, so I'll draw the ground. All right, and you're gonna have gravity, and you're gonna have this, but now we're kind of getting into our free body diagram, which we're not intending to. Right. So, yeah. So here, let's do this. That's maybe what I would do for that. All right. So now a true free body diagram. So we're going to do it for the load of wood. So it has some gravitational force, some normal force, we can label that, and then it has this tractor pull force, and it is at some angle here, phi, with the horizontal. And I'm going to guess this is a nice direction for x, and this probably won't matter, but this is the nice direction for y. Why doesn't y matter? Well, if we're computing the force, the direction of motion, I'll use this color here, v is this way, right? So it's traveling to the right. So we're only concerned with the component of force that's traveling in the that is pointing in the direction of travel. So this here would be, if we're labeling this F, then this here would be F cosine phi. Alright, so now, as usual, we would find the sum of the x and the sum of the y, but really for this all we need is this sum in x, because we only care about the x component. So we've already kind of done it, but the sum of the forces in the x is just equal to F cosine phi. This force does not contribute. This would be mg. This would be the normal force, but we don't care about it. It doesn't contribute. So now that we found the net force in the direction of travel, we can plug things in, but we might as well just go all the way symbolically. Then the work is going to be equal to this net force in the x direction rather, times the displacement s. Alright, so what are our numbers? So that's so F cosine phi with an extra s in there. I'll just do it back there. So s is, what is it, 20 meters? 20 meters. The magnitude of the force from the tractor, 5,000 newtons. Cosine, the angle, which was 30 something, 36.9 degrees. Make sure you're in degrees and not radians if you're plugging in degrees. And so you should get that the net work, or the work done, is 10,000. What are the units? We have Newton and meters. Newtons times meters. Well, it turns out that there's an SI unit that compounds those two. A Newton meter is equal to a joule. So 1 joule, it's written this way, similar to my name, but it's not, is equal to 1 Newton times 1 meter. Yeah? Or in other words, 1 capital J for joule is equal to 1 Newton meter. And so we can use our prefixes also and say that the work is equal to 10 kilojoules. Joules is the units for work. It's also the units of energy, and that's what we're talking about next video. We're going to talk about kinetic energy and the work energy theorem. Right?